each by themselves. So, you know, using a combined, like coordinated motion of each independent wheel, this allows us to do that. It also really helps us. One of the ideas is load balancing. So making sure one side of the rover is not digging in on, you know, and we try to keep the weight on each wheel balanced, which helps overall, you know, mobility. You know, one of the things we think a lot about, we worry about, is slipping, so that we think we're moving, but we're not moving, and that can be tricky to understand when you're in a control room here on Earth, and you're watching, you know, just images, just static images coming down. But we have a lot of good techniques to help us understand how our progress is moving across the surface.
That's good. We don't want a lopsided rover.
You also mentioned navigation. So we have a few instruments that help us understand where we are and also where are we going. So if you look at here at the front of the mast, we have 2 cameras. So those cameras are the main ones that the drivers use to image the environment and see what's in front of us. We also have 4 more cameras, 1 in each wheel. We call them the hazard cameras, so they look at potential hazards around the wheels before we actually go ahead and drive. We have a couple of cameras on the back, on the rear side, that we call the aft cams. And those are like in case that we actually need to drive on the rear-wise, we can see what's, exactly. We can see what's behind. And then another very cool component that I always give a lot of importance is the star tracker. So if you recall how the old navigators and sailors used to navigate the oceans, it kind of works similar. So the old sailors, they had maps and with constellations and stars, and so they used to look at constellations and compare it with a map and say, okay, I think we're heading north this way, right? So the star tracker does something similar. It has a camera and it's going to take a picture of the stars, and then it's going to try to recognize some of those stars and compare it with a star map that it has. And in a similar way, it's going to try to say, okay, those are those 3 in my map. Okay, I know where I'm heading. So the star
star's
tracker,
always guiding us.
Exactly, it's guiding. It's guiding.
That's awesome. Well, we've had a lot of questions. I know that we can. A lot of our viewers may have a lot of questions too. Should we check in?
Yeah, let's check in with our audience and see what questions we're getting.
So here we have our Top 77 says, I'm curious to learn more about VIPER's lighting system. Mercedes, if you want to answer that one.
Sure. So we have LED lights on the front of the rover. These lights might be used whenever the scene it doesn't have enough brightness. And so one very interesting thing about the VIPER mission is that it's been a very high challenge to design the cameras and the lighting system, because there's no atmosphere on the moon. And so there's no scattering thanks to that atmosphere that kind of makes the light bounce around and in the end ends up illuminating the shadows. Here on Earth, you can see, you know, at sunset or whatever, you can see your shadows. And you can still be able to tell what's on the shadow. You see like little pebbles or whatever it's on. But on the moon, because there's no atmosphere, no scattering, the shadows are really like pitch black. And then the rest of the environment, actually the moon is fairly reflective, so it's very bright. So the scenes that we're trying to image are very high contrast and very high dynamic range. So it was a challenge to have a camera system that is able to capture those scenes. And in the end, what we want to do is see, right? See features, see what's hazardous or not. And so the lights are going to help with this whenever there's not enough light.
Strategic lighting.
And especially also when we go into permanently shadowed regions, there's no sun availability. We have calm, but no sun. And so we need a source of light to illuminate the scene.
One of the cool parts about our lights is you can pick what wavelength of light, you know, what color you want to use, and we've found that given the scene and the environment that we're in, it's a particular shade of blue for us. So we'll blast a very bright bluish light, and so like when we see it in test labs,
it in the test videos,
it's a little surprising that it's not like a flashlight that you think you'd normally see. It's a specifically tuned wavelength of blue light that helps make sure that we can get the most information from the scene that we're trying to use. Because we use our two cameras in conjunction with the lights to recreate the scene in stereo and recreate 3D maps that helps us understand where the hazards are and where the good places to drive
It's
are.
like the rover's eyes.
That's right, just like ours.
Yeah, we have also some more like comments. Sir Salty Bacon says, NASA is so cool. And Dr. Blue says, my dream is to work with you guys.
That's awesome. And we have Sonar Blips who has asked, back to that snoot, there's some questions on it. How does the snoot clean itself?
The snoot does not clean itself. The snoot is clean, very clean right now in that clean room. We are very, very careful about cleanliness. And it's actually, that instrument, IMSolo, is one of our most sensitive science instruments. And so we take a lot of precautions to make sure that it stays clean through the build and in the integration and testing process. It's also it's not fully exposed outside of the rover. It's pretty far, it's in there. So there's a little hole at the bottom of the rover, and that's what these gases will come up in through the hole. And so I think it won't really get, and again, we're not moving very fast, so this is another somewhat misconception. By the way, if you see these lights going off, it's probably because we're getting ready for some solar panel testing.
Oh, cool.
So that's what's happening over there.
What can we expect from the solar panel testing? Like, will we be able to see anything
It doesn't look like it's in the view here, but they are testing out the response of the solar panels, making sure they're seeing everything they expect to see. So they have special lights that they use to inspect the solar panels. So you have to get rid of the shop lights, the clean room lights, to be able to get that clear signal from the lights that they use for the test.
Yeah.
But anyway, so the snoot stays clean. We're not moving fast, so stuff's not getting kicked up in there. But in general, we are very careful overall about cleanliness. We don't want to bring anything from Earth that will mess up our measurements.
And we'll talk some more about that. Should we take one more question?
Yeah, I
from
see
our
an
audience?
interesting one. How much pressure can the rover handle?
Pressure as in environmental pressure?
Well, so
explain
yes. Well, I'm gonna guess a little bit. So it's when it's on the moon, it's in a vacuum, so there's no pressure, which is different from on Earth where we have 1 atmosphere of pressure typically. So it can handle 1 atmosphere of pressure pretty well, and on the moon it's got no pressure. But there's but it's also sitting on the surface of the moon. It's driving around, but because the moon has less gravity than Earth, right? It's about 1/6 of the gravity we experience on Earth. The whole rover is actually lighter on the moon. So on Earth, it's about 450 kilograms. So on the moon, it's a lot lighter. So it's a lot less ground pressure, and so on each wheel there's less pressure, and it's actually only designed to rove on the moon. It's not designed at all to rove on Earth, so we can't drive this the
We're
flight
not drive
rover on
testing
Earth.
it here on Earth.
So we're testing it as you talk about.
Yeah, we tested it with McGrew, is the mobility platform for VIPER, and so it's basically a 1/6 mass version of VIPER, but it only has basically what we need to drive. It has the motor controllers, it has the wheel modules, the wheels, and then some like the IMU, another component we use for driving. But we've done like very extensive testing. But it's true that here this VIPER rover on Earth is very loaded. Like the poor thing is actually withstanding a lot of load. It's going to have an easy time when it gets to the moon. It's going to have like 1/6 of an easy time.
Funny. Well, for those of you joining, if you're popping in on the live stream now, you're watching the build of VIPER, NASA's first robotic moon rover, and we're joined today by VIPER experts who are answering our questions and hanging out, and we're watching the live stream, and it looks like maybe there's some solar panel testing that's coming up. But Ryan, you have been in the clean room of the build. Can you tell us more about the clean room? I mean, what that means, clean room, and then like suiting up. We saw people suited up with all sorts of gear.
Yeah, as I was saying, since we're so careful about contamination and dirt and anything that'll mess up what we're trying to do when we get there, we have to keep it in a very clean environment. We have to make sure that it's not getting anything that'll mess up the cameras or the science instruments, or get in the electrical connections, or mess something up. So it's a controlled environment. It's as you say, it's a clean room, and people wear these outfits because we actually are pretty dirty beings. So we try to limit the amount of stuff that people bring into the room, that so they can't, they won't add to it or make it harder. So we wear these jackets. They basically just cover our clothes, and there are specific fabrics to make that don't shed, and that keep things on the inside. You wear a hairnet. You don't want to get hair on anything. If you've got a nice beard, you wear a beard net, because you don't want to, again, you don't want to shed hairs. But we limit a lot of skin shedding, like
contamination.
Yeah. So that's a big part of it. It's also interesting because it smells. It smells different than,
you were saying
it used to. It's not
like?
Because it's so clean. It smells like absence. It smells like something's missing. Normal things that we take for granted and we don't think about. When those things are gone, you actually think about it. It's weird. It's the opposite. So you get in there, and but it's good. It's a work environment, and we're doing something really important in there. So going in there, getting the clothes on and the hairnets on. And the shoes. I missed the shoes. We have like a vacuum, like you stick your thing in and it scrubs your shoes and vacuums at the same time.
Not everyday booties, right?
and then you like step on the sticky stuff to get anything on the bottom of your shoe, and you get the shoe cover on. So it's all part of that, but it's intentional because we're going in there, and we're thinking about, we're being really careful with what we're working on, and trying to make sure that we handle it carefully. We treat it with care, and we're careful when we install everything. So it's an environment controlled for the purpose of controlling the environment, but I think it also gives you an intention, a feel of going in there to do this important work and to be aware of what you're doing, because it's part of the process.
And for those just joining the watch party, can you tell us about the VIPER mission objectives and goals? Mercedes.
Yeah, so I guess in simple words, what we're trying to do is we're trying to go to the South Pole of the Moon and look for water and other resources. But specifically, we're trying to understand where is that water and resources, how much of it there is, and then actually how deep do we find it? Do we find it kind of like superficial at the surface, or like as we dig deeper, do we find more or not? So in the end, kind of like the product that we're trying to develop with this mission is a resource map. And hopefully we are able to extrapolate it to the rest of the moon as well.
And why is it important to answer these questions?
Yeah, that's a very good question. So water is a very important resource, not only here on Earth, but also for space, or in space environment. And the reason, you you can guess it, we need it for drinking, for sustaining human life. Also, there's oxygen within the molecule of water that we can eventually extract, and we need oxygen for breathing. So for life support of astronauts, for any kind of space operations, they will need water and oxygen. Also, the molecule has hydrogen, so hydrogen and oxygen are one of the main rocket fuels. And so if you recall, rockets here on Earth are huge, mostly because 90% of it's fuel. And then the other 10% is the structure and whatever you're carrying, like a satellite or a probe. And so we use that 90% mostly just to fight and escape the gravity of Earth. And then that's
so that
it. Then you have a little bit.
To go up, right?
Yeah, exactly. And then you have a little bit just to move around, right? But imagine if you could actually refuel that rocket somewhere else after spending all that 90%, right? That would enable going much further into the solar system and also outside the solar system. So that's one part of it, which is, it's important for space exploration. but it's also important for science. So there's still, the scientific community still has a lot of questions that are not answered fully yet. And so for us to understand how did, for example, water get to the moon in the first place, or once that water or other resources are on the moon, how does it transfer and move around the moon to different areas? Like what mechanism is the one that transfers that water? And once it's there, can it escape again and go to a different place? And if so, where? And like how does that happen? So like really the moon is a treasure chest of science, and is very valuable for the scientific community. And this will help understand how the solar system was formed, and Earth was formed, and the moon was formed. So it's also very important for that.
Yeah, one of the keys to understanding the water, this is kind of like a first step to, say, use it as a resource. You know, we've seen things from orbit. We know there's signatures of water and hydrogen from orbit, but nobody's really been down to this kind of location where we think it's likely that water is in useful concentrations, more or less in different areas. That's what we're going to explore. But it's that link between, you know, remote sensing and ground truth. And that's what we're doing. That's why we're going to the ground. That's why we're roving around to get a human scale idea of, you know, where is the resource and it leads to the next step of then how do I extract the resource? How do I make use of the resource? And you need to understand where it is, you know, how accessible it is, how much it is to have a really good idea of how you would then go get it. But that part of, she explained the two different sides of it. It's science enables exploration, and exploration enables science, right? They're both
interconnected.
They're, hand in hand, and this does both, right? We're understanding this process of how volatiles and water get there and move around, and we're also understanding how then we could use it and enable future science and exploration farther out in the solar system.
And that's what we do at NASA, right? Explore the secrets of the universe. And so VIPER, we're targeting 2024 for launch date. Where is it headed to? I mean, we know the moon, but can you tell us more about the location it's headed to?
Yeah, so so going to South Pole. Again, the polar regions have these really interesting thermal environments that water can be stable in ways that they can't be stable in the equatorial regions, where a lot of past missions have gone. So we have to go to a polar region, and the South Pole is an area that has got a lot of interest lately, and not only for the resources that may be there, but just the unique environment and conditions. So we need to go there to learn about that environment, not only for the resources, but learning just how it is there, you know, and informing future missions, you know, what to expect. So we have picking the actual landing site and traversing for VIPER is pretty complex because you have a lot of constraints. We're a solar powered rover, as Mercedes said, and so we depend on sunlight. So you need sunlight, right? Obvious, right? And then, you know, it's a rover, right? We can't just, you know, scale vertical walls. We have limits to how, you know, how steep a slope we can be on. So we have to make sure we understand the slopes. We are a direct-to-earth communication system. There's no relay right now, so we need line of sight to Earth. So these are some basic constraints, you know, hazards, but then you have to lay on things like, you know, are you going to places that have expected measurements, you know, that you want to get? So you're laying this aspect of, you know, the mission objectives among the engineering type constraints. So you combine all that, and you have to pick very carefully where you're going. Landing sites, you want somewhere flat, right? Somewhere with no rocks or craters, which is hard to find on the moon. And so, you know, all those things. But we've found a lot of candidates, and, you know, we rank them and we test out different traverses to make sure that, you know, we have a lot of confidence that we're going to be able to get the measurements we need. So our landing site, it's in a recently named area in the South Pole called Mons Mouton. And it's near one of the pretty big craters there, in a Nobile crater, and it's kind of a mountain, flat mountain near the crater. This area was really good for us because it has good sun, good communications, good slopes, but it's also near a lot of good permanently shadowed regions of different sizes that we plan to go inside and explore nearby each other. And it also has these unique areas. Our mission is about 3 or 4 months long, and it's driven by the seasonality. Like on Earth, if you're on the North or South Pole, there's a summer and there's a winter. And in the summer, the sun's, above the horizon, kind of skirting along. And the winter, the sun's below the horizon all the time. So we don't want to go in the winter. It's actually very similar on the moon, right? North Pole,
Seasonal,
South Pole.
yeah.
It's seasonal like that.
Yeah.
So we want summer on the moon summer,
Yeah.
moon South Pole summer. That's what we want. And so the sun is up, and then we need to have the communications, and so it's actually one interesting part is the communications, the line of sight to Earth. The moon wobbles a little bit, and so it wobbles kind of in the wrong way, and basically the Earth line of sight to the Earth goes below the horizon, so we lose communication. So we're actually doing, over these 3 to 4 months, we do 2 weeks of activity, and then the Earth sets from the rover's point of view, and we kind of just sit there. But where we sit is important because for these 2 weeks we can't. We're solar powered, so we have we have to be in a spot that's getting sun. So we're parked. We're not moving, but we need sunlight to keep the heaters on to not freeze. So shadows can be moving around the South Pole at these high latitudes. The shadows move pretty quickly. There's a lot of mountain ranges. The sun is low, so it'll hit a mountain. It'll be clear. It'll depending on where you are. So we have to pick a spot to sit for those 2 weeks, so that we minimize how much shadow period that we encounter. And we have, and
it's all very
this
calculated
region,
and thought out.
Yeah, this region we plan to go to is one of those. Also has a lot of good places to sit for 2 weeks and minimize the shadow. And so we've designed our traverse to go where we need to go, and then when we're out of communications, it'll sit getting sunlight, happy for most of the time. And then we get communications again, and we keep going, collect all our data.
It's a good thing we want a happy rover.
So me, I'm seeing a lot of questions coming in from our audience.
Well, it's thank you for all the audience engagement that's happening. Let's take a look at what they're saying.
Yeah, there's this question. Will this rover travel fast to reach a target?
I mean, it's one of the, I think it's the fastest rover so far, but it's not as fast as you would think. It's, I think the max speed is 20 centimeters per second. But you also have to think that we're doing waypoint driving. So basically, you start from a point A, where you are static, you take pictures, you look at your environment, you downlink all that data to ground so that we can assess everything's safe, everything's good. And then we decide, our drivers will be there looking at those images, and then they're going to decide, with the help of the scientist as well, they have a scientist right next to say, go find that spot, based on the science data that they're getting. And then we'll drive to a different point, and that's a new waypoint. And then at that new waypoint, normally those drives are between like 4 meters, maybe at the most 8 meters. And then we stop again, and we redo images, data, and so basically that takes time, right? Like when we stop and check that everything's good in images, that takes more time. So it's not 20 centimeters per second, we're going a little slower than that, and also we have to be kind of like tagging around craters and rocks and slopes, as Ryan was saying. So yeah, like we're fast, but not too fast.
we do need to cover a lot of ground, so it's important for us to. We're always watching how fast we can go and how we're operating. But I think overall the amount of ground we'll cover in the time that we have is pretty fast for a planetary rover.
Yeah, absolutely.
And maybe relating it to the safe havens, which are those spots that Ryan was mentioning, that we need to be at, so that when the lunar night or darkness comes, we're minimizing the amount of darkness that we have. We need to be there by the time that the lunar night catches with us, right? So we do have a timeline that we have some margin on that timeline, but we need to accomplish that timeline.
And that piece of it. So we have a question regarding the autonomy of the rover. What level of autonomy will the rover have, if any?
Yeah, it's not too autonomous. So there are things that are happening on board. One of the things that it's unique to this mission, the moon is pretty close to Earth relatively. Some of the other missions that do rovers, like Mars missions, for example, the light travel time is significant, and so it's not really realistic to have this real-time driving and iteration of looking at data and reacting to it. So we will do a lot of real-time stuff, and we split what's on board, what computation, what activities are happening on the rover with what we can do on the ground. And because we're so close, we move a lot more computation and decision-making to the ground, so it doesn't need to be as autonomous as some of the other planetary rovers. So we consciously made that decision, and we have this interaction with operators and the rover working together, every minute. So it's a little less autonomous than others, but we also take advantage of that by having this real-time science and data evaluation while we're roving, and can react to what we see and where we go, and with the scientists and the engineers working together.
Yeah, and if you think about it, it's, as Ryan was saying, is a whole trade. Like, if we don't have that much complexity on board the rover, things are less complex, less failure modes. We take that complexity on ground in that sense. And then if you can think of like level of autonomy as well, we are normally automating things that are related to safety. So if something bad goes on the rover, there's still some level of automation to prevent things from going pretty bad. Like, there's a short circuit, there's like we lost communications, and the rover is by itself, so we have a few responses that are automated on the rover for safety.
Basically.
Yeah,
That makes sense.
And we'll take one more question. How many people are working on this project? I know there's a lot of teams.
Yeah, there's a lot of people. Yeah, anything like this, it takes a lot of people and a lot of different skills. It's hard to say a number because it's a matter of what part of the group do you consider. Like within NASA, and there's probably 500 or something like that that have been involved. But it can go bigger than that because we get a lot of components from industry, and so we get something from here or there. People are working on it all over. So I think the number is probably bigger than that. If you actually, all the people that contribute to something like this, it's a lot of people. It's a lot of effort. Yeah.
Wow.
It's one big team effort. Yeah.
Absolutely.
Yeah. So how about we check in with our rover and
Yeah.
see what's going on? We're seeing some action happening.
Yeah, you see they're taking some
They're
pictures.
documenting.
Yeah, it's always important to when you're closing things up, or you're trying to investigate or share what you're seeing with others. Documenting what we do. So yeah, I think that the things we've been working on lately with the rover are checking out these electrical connections. It's been some of the first times we're bringing these flight pieces together in their flight configuration. So we gotta make sure that we're getting the same expected performance out of each box that we're expecting. And a lot of times the first time you do something, you might run into something you didn't expect, and we usually we don't want to be too fast about it. We don't want to miss anything, or if Mercedes was saying, if you start building it up, it can be harder to get back in to diagnose something. So we just try to be really methodical and careful with what we see, how we react, and make sure we're good to continue forward. So right now, I think they're checking out those electrical connections on these first components that have gone in, and they'll go in there, check connectors, or they'll go in there. Take measurements with checking each wire just to make sure it's getting expected signals, and so yeah, it's precise work, and it just takes a lot of time.
Yeah.
When is it expected to be completed, and what happens after it's built?
Around January, something like that. January next year, right?
Yeah, yeah.
Early next year?
Yeah, so it'll come together pretty quick, and then we'll do the system tests. So that's kind of the next step, is once you get it built and it looks like this, you'll start putting it through its paces as a system in the environments, and then we get integrated. This VIPER rover will be delivered to the moon by a CLIPS partner. This is a Commercial Lunar Payload Services. So NASA has basically bought a service to bring something to the moon. And in the past, a lot of them have been payloads, smaller payloads. But in this case, they bring in the whole VIPER rover to the moon.
They're waving over at us. Yeah,
Astrobotic is building the lander for VIPER, and it's their Griffin 1 lander. So we essentially deliver.
Oh, there's another person there.
Yeah,
Hi.
Yeah, we deliver the rover to basically to the lander partner, and it'll get integrated with the lander. We do some checkouts there, and it gets integrated onto a launch vehicle, and processed on the launch pad, and then it'll launch.
Yeah, we're continuing to watch
Yeah,
the
like
different
I just
testing that they're
rolled in there.
doing. Yeah,
Something under there.
is that part of the solar panel testing? We think is that.
I am not sure.
Hard to tell what's in
You can
there.
see,
Yeah.
you can see
Maybe I'll
like
wrap it there.
that's like putting things in these bags, right? We try to keep them. They're like electrostatically protective bags, so you don't get discharges, shocks, or discharges, and it also keeps them clean. Often we put 2 bags around something just to make extra sure.
Oh,
It's a wheel module.
Oh,
Yeah.
wow.
Okay.
And the wheels are always a popular
Yeah.
topic of discussion.
On social media,
Yeah.
they always are like asking about what's the design like, the wheels. So
Yeah, so this is going to be this is actually a engineering model wheel module. The flight wheel modules are already on the chassis behind him, but this is an engineering model, and I think oftentimes we'll use these to check something that we're seeing on the flight vehicle and make sure we're seeing the same thing on the test hardware.
yeah.
But it's a flight-like component, so it behaves just like the one on the rover.
I was like opening a present right now. Like
Yeah.
Unboxing.
surprise unboxing. Yeah.
Those actually, so that part, that the wheel,
Yes.
what we call the wheel module, has the 3 actuators. So it has the one that steers the wheels. It also has a motor to flex up and down the suspension, and it also has the propulsion motor, which is the one that actually moves the wheels
Yeah.
to produce traction.
Yeah, what are some of the innovations like in technology that the rover will have?
Yeah, I think it's mostly the combined system. There's not a lot of new technology. You don't generally, you like to use things you can rely on.
Yeah.
There's definitely areas that whenever you build something specific and custom, there's some development in how it's built and making sure it survives the vibration environment, the thermal environment. A lot of the innovation and work has been to build these custom things. Some of the things are more off-the-shelf, typical space flight hardware type things, but I think we talked about the mobility system quite a bit. This is the first time this kind of mobility system will be used on a planetary rover.
Inch warming.
And it's for a purpose, right? It's to match the environment that we're going to, and to it's all about the idea of covering distance and not getting stuck, and the uncertainty in the environment. So I think our mobility solution is pretty unique, and something we've tested quite a bit with our test hardware. And I think the other key part of this is probably the thermal. It's a really challenging thermal environment. It gets really hot. It also gets really cold, especially in these permanently shadowed regions. As you were saying, the temperature,
that's a key thing.
it gets really cold. So the idea of being okay when it's really cold and also being okay when it's really hot takes a lot of purposeful design. We have a warm box on the inside that kind of keeps all the heat inside, and that panel that's on the back is one of the components of that warm box. So there's 4 sides to it, and then so that keeps us warm when we don't want to reject, when it gets really cold, we can keep all our heat and all our electronics warm and happy. And then, when we're in the sun, or we get sun staying on one side and heating up things, we want to be able to reject that heat. So it's kind of the opposite. You can design for one or the other. We need to design for both. So we have a radiator on top, which we talked about, and this warm box on the inside. So there's a connection between the warm box and the radiator. We have a system of pipes that can have a working fluid in them, and it basically brings heat up to the radiator to reject. But we have the capability to essentially cut that flow off to not let the heat go out and escape through the radiator. So it is something that we control depending on what environment we're in. And that's been quite a design and hardware challenge. So that whole system working well and surviving all the environments and performing as expected. So that's another innovation for sure.
It's like all the action's happening right now.
I know.
As we're watching. Yeah.
You see that panel that Ryan was pointing is basically one of the, in some way, walls that form that warm box. So there's going to be 4 of them, one on each side.
Oh, okay.
So it's just, you see the computer there, I think, and I think it's also nervous, and the computer are basically glued to that heat spreader in a very conductive way. So it's very easy to transfer heat flow from that computer to that wall. And then from that wall, it goes into the pipes that Ryan was mentioning. And from the pipe, it goes to the radiators here.
Okay.
And we can radiate. And the pipes are designed so that they passively, we don't actually control that, they passively cut the flow when the components are getting too cold. So we don't radiate that heat up. So it's smart design.
Yeah, I was going to say, so it knows when to do that piece of it. Wow. So it looks like they're getting ready to test or install.
Yeah, I think they're using that test wheel module to, again, that they're going to check to see if it's getting the same kind of performance that the flight one is. I think they're diagnosing something in the harness of electrical connections. And using that, it is really smart to be able to, and have that capability it's good for us to be able to make that comparison to make sure we understand what we're seeing on the flight vehicle. So I think they're bringing that in there. Looks like trying to get it close so that they can actually make a connection. Yeah, it's just part of the investigation, if you will, in the process. All those, like, there'll be other 4 panels coming in. That's why it kind of looks so chaotic, is there's a lot of wires that are not, in their installed position yet, so they kind of are waiting for their turn. But when you route them, you can see on that back panel that everything gets cleaned up, and the harnesses are routed pretty clean. And they're tied down because things will be shaking quite a bit during launch. And you can see
rattled and moved around. Yeah.
You can see the kind of wire that's coming off from the left to one of the workers in there. That's it's a grounding. There's a electrostatic discharge prevention. So you ground the body. You have a wrist strap that connects your body's electrical potential to a grounding in the facility. So you see, anytime they get close to the hardware, they have these ground straps plugged in and attached to themselves to prevent any kind of discharge into the electronics.
Safety first.
Yeah.
Amazing. So we also wanted to ask you some personal questions, and we wanted to get to know you better. What inspired you to work for NASA and the VIPER team?
For me, I guess I always remember what my dad told me. Since I was a little kid, I was one of the NASA fans. My dad always tells me, when you were a little baby and I was going for a walk with you on the baby stroller, you would see the moon, and then would you try to catch the moon, and I would have to go after you because you were already able to walk, and you would walk on the street. So I guess that transferred to this moment right now. So it's pretty.
Always going for the moon.
Amazing, yeah.
That is amazing.
But honestly, if I have to say one thing that I like about working at NASA is the people. I feel like people is just great, and Everyone is great in their own way, and very passion. Like they have so much passion for what we're doing. So I think we feel that in the environment, and you're happy every day when you go to work.
Yeah.
Because everyone's happy and has so much passion. So.
Yeah, ever since I was a kid, I mean, probably not uncommon, but I'd watch science fiction, watch Star Trek, Star Wars, growing up. But especially like Star Trek, like it's about
Yes, right.
it's about yeah, I can't do it every exploration. Understanding what's out there, and just space always attracted me because it was, it was such an unknown, and it's such a foreign. The environment is so different that it just leads you in directions you wouldn't think of, and it's very exciting to me. And I was always kind of engineering oriented. I loved aerospace. I loved space, and just getting involved in a project like this. It's definitely a dream. I mean, I feel pretty lucky to be involved, and to be able to contribute to understanding and exploration and knowledge. It's really nice to have that link to your something you work on, you spend a lot of time on, and have the people to work with that have a similar drive and energy and care about what we're working on. But it doesn't have to be engineers. Like we have so many different types of people and skills that work on this project. I mean, there's obviously engineers, there's scientists of many different kinds. There's people who do stitching of like the blankets I see. We have a lot of like organizers or people that help to set things up for us, or people working on the facilities. There's technical people that just do like working on machinery, or work with composite glues, or there's just so many different ways to be involved. Obviously computer science, and there's a lot of software, even graphical design, outreach. I mean,
so many different
there's a lot of ways. It's like you can be excited about anything, almost anything, and be able to contribute to something like this and come be involved.
Yeah. It's an exciting time at NASA as the rover's going to the moon, and we're the Artemis generation, and the first woman is going to the moon, and the first person of color. Can you tell us a little bit more before we head out on the connection between VIPER and Artemis? Mercedes, do you want to share this a little bit?
Yeah, so as we were mentioning, VIPER is going to produce this resource map, right? Like we're trying to understand how much of it, where is it, how deep. And so all these products, all this data is going to inform the landing site selection of the future Artemis crew missions, right? They might want to go to areas where there are more of these resources. So this is like the direct connection with Artemis program.
Yeah, I think working in this environment, understanding it, there's almost like reconnaissance. Like, what's it look like? What is this? What is the sun? How does the sun look like? What's the temperatures? What does the dust do? So it's kind of like good for people to understand the environment they're going to be going to, and no one's ever been there. What's a PSR like? What's the regolith like? Am I going to sink my foot in there? It's really important, I think, for the astronauts to know, have some idea of what they're going to encounter at these South Polar locations.
Yeah, absolutely. Great. Well, do either of you have any final words for the Artemis generation? Anything you want to share for anybody that wants to dream of working at NASA? Ryan, I want to start with you.
Yeah, just come get involved. There's no barriers. You can, hopefully, like you can do this. You can do this kind of work, and no matter what your passion is, as long as you're excited about it, come work, come be involved. It's possible.
I love that.
Yeah. I would say that if you have a passion, you have a dream, go for it. Don't let anyone tell you to not go for it. It's possible. We have the education. The public schools are good. go for it, and make sure you work on something that you like, because you're going to spend a lot of hours across your entire life, so you better like it.
Yeah.
And talent is only a small part of the equation. In the end, hard work and perseverance is what matters. You know, I was a good student in college. I was not the top #1 student, but I was definitely one of the most perseverant ones. So persevere, hard work, and pursue your dreams.
Amazing.
Yeah, that's amazing. And you both, thank you so much for being with us today as we've been watching the live stream of the build of the VIPER rover. And just so grateful for your knowledge and for your inspiring words to the Artemis generation. And you can continue to learn more about the VIPER mission by checking that out at nasa.gov/VIPER.
And we will be following, of course, the VIPER builds and keeping you updated along the way. Make sure to follow us on our social media platforms at NASA Ames. Until next time.
Bye, y'all. Go VIPER.
Bye.
Go VIPER.